Well, hello everyone. In this video, I wanted to make an introduction into how we can work with how can we solve exercises related to DC motors. For example, in this exercise, we have the following information. We know that a DC series electric motor is spinning at 4,500 revolutions per minute, draws 3 amperes of current with a 110 volts measured at its terminals. The resistance of the armature windings measured with an ohmmeter when the motor is at rest on power is of 2.45 ohms. How much counter electromotive force is the motor generated at 4,500 revolutions per minute? So, well, I think that it is better to look first into the data, no? We know that the speed of the motor, based on the data given by the problem, is of 4,500 revolutions per minute. Also, we know that the motor is demanding a current of 3 amperes. I wanted to mention that this 3 amperes current is basically the armature current, and that the applied voltage to the motor is 110 volts, according to, well, measuring its terminals. And also we know that the armature resistance, okay, is equal to 2.45 ohms. Okay, this is the data of the problem. So, well, I will try to solve this exercise, and I will share my screen with you. Just one second. Just let me change the screen of my tablet. And here, well, we have the screen of my tablet. It is sharing, just one second. Okay. So this is my tablet screen. And I think, well, I have placed here the data of the problem. And I just want to increase a little bit the font size. And, well, I think that the first step to tackle this problem is as follows. Remember that, well, according to the problem, we are dealing with a DC series motor. So for a DC series motor, we know that we have the voltage source, then we have the armature resistance, and well, we have also the back EMF voltage. Okay. And we need to compute exactly this value. No, what is the back EMF voltage? Also, we know that the voltage that is applied to the motor is 110 volts. This is the direction of the current, that is 3 amperes. And well, the resistance is equal to 2.45 ohms. Okay. So basically, we need to solve the circuit in order to compute the back EMF voltage. But the first step is to, well, draw the circuit of the DC series motor, and then we can apply the Kirchhoff voltage law to this loop. So if we apply the Kirchhoff voltage law to this loop, we have the following. We have minus 110 volts plus 3 amperes times the armature resistance, that is 2.45 ohms, plus the back EMF voltage, and this is equal to 0. So, well, solving for this exercise is relatively easy. Well, if you solve this equation for the back EMF voltage, you will obtain a value of 102.65 volts. Okay? So at the end, this is the result. So as you can see, the first step is to identify the data of the problem. And based on that data, we can draw the circuit of the motor. Remember that we start with this small circuit. There are some cases in which they can tell you that you are working with a shunt motor, but regardless of that, this is the base circuit, okay? You always need to draw first this circuit, and based on that, we can solve the exercise, okay? So, well, let's make another exercise. So I will stop sharing my screen, and I will share the screen of the PowerPoint presentation. And okay. So again, we have another problem. Here in this problem, we have the following information. We know that the induced electromotive force in a permanent magnet DC machine is 200 volts. So we know that the back EMF voltage, no, the induced electromotive force is the back EMF voltage, that is 200 volts. Also, we know that the speed in revolutions per minute is 1,200 revolutions per minute. And also, we need to calculate the electromagnetic torque, okay? And also, we know that the armature current is equal to 15 amperes, okay? So based on this data, we need to compute the electromagnetic torque. So what you can do to solve this problem is as follows. Let me share again my, the screen of my tablet. Just 1 second. Let me go to my tablet. I need to share it again. Just 1 second. Well, we need to wait a little bit until the connection is established. Okay. So, well, this is my tablet. And again, I have I have right here the data of the problem. We know that the back EMF voltage is 200 volts. We know that the speed in revolutions per minute, just 1 second, revolutions per minute is 1,200 RPMs. And also we know that the armature current is 50 amperes. So what we need to do in order to solve for this exercise is the following. We need, again, to draw the circuit. Okay, that is the first step always. So we can draw the circuit. I think that is not necessary, but for a step, I think it is important. No? We can always draw the circuit. We know, we are applying certain voltage to the motor. We know the armature resistance that is like in this part. And also we have here the back EMF voltage, okay, with the following polarity. This is ground. And what else? Also, we know the armature current, no, is the current that is flowing through the circuit, that is 50 amperes. So based on this data, we need to compute the electromagnetic torque. But what you can do, we have some relationships. For example, we know that the mechanical power that the motor can provide is equal to the electromagnetic torque times the speed of the motor. But this speed needs to be expressed in radians over second. Also, this is equal to the back EMF voltage times the armature current. Okay, so we need to use these two expressions. Okay, we can compute the mechanical power by taking the electromagnetic torque times the speed of the motor, or we can use the back EMF voltage times the armature current. Okay, so what we can do to compute this electromagnetic torque is the following. We know the back EMF voltage, and also we know the armature current, and also we know the speed, but we need to convert this speed in radians over second. Okay, so there is a conversion that we need to make, but we can find a relationship for the electromagnetic torque as follows. The electromagnetic torque is equal to the back EMF voltage times the armature current divided by the speed. Okay, so we can substitute the data that we have. We know that the back EMF voltage is 200 volts. Also, we know the armature current. And this is divided by the speed of the motor. And that is 1,200 revolutions per minute. Just take into account that we need to convert this speed into radians over seconds. So to do that, we can do the following. We know that 2 pi is equivalent to 1 revolution, and 1 minute is equal to 60 seconds. So if we can compute the electromagnetic torque as follows. So if we solve for this, if we compute this expression, you will have that the electromagnetic torque is 23.87 and 32 newtons times meter. Okay, this is the electromagnetic torque. Let's make another exercise. Let me share my screen, my PowerPoint presentation. Well, in this problem, we have the following information. We know that the armature resistance of a DC motor is 0.5 ohms, okay? So the armature resistance is equal to 0.5 ohms. Also, we know that the armature current, according to the problem, is 20 amperes. And, well, from 220 volts mains and is running at a speed of 80 radians per second. So this 220 volts mains is basically the voltage applied to the motor, that is 220 volts. And we know that the speed in radians over second is 80 radians over second. Okay, so we need to determine the induced electromotive force, electromagnetic torque, and the speed of the motor in revolutions per minute. Okay, so again, the first approach is to draw the circuit. So let me go again, go back to my tablet. Let me share my tablet again. And just 1 second. Okay, so this is the information that we need. Okay, so, well, I need to draw the circuit. So we have the circuit right here. Okay, and we know that the voltage applied to the motor is 220 volts. We know the armature resistance, that is 0.5 ohms. I know this is a 5. And here we have the back EMF voltage. Okay, let me draw this better. This is the back EMF voltage. Okay, in this part, the back EMF voltage, and here we have the other part of the circuit. And the back EMF voltage, we need to compute that, no? This is one of the aspects of the problem, no? We need to compute the back EMF voltage, and also we need to compute the electromagnetic torque and the speed in revolutions per minute. So we can compute the back EMF voltage. We know that the current in this circuit, or the armature current, is 20 amperes. So we can apply the Kirchhoff voltage law to this loop. So we will have minus 220 volts plus the voltage drop in the resistor, that is 0.5 ohms, times the armature current, that is 20 amperes, plus the back EMF voltage, and this is equal to 0. So the back EMF voltage is equal to 210 volts if we solve for this equation. Now we need to compute the electromagnetic torque also. So we need to use the mechanical power. We know that the mechanical power is electromagnetic torque times the speed, and this is equal to the back EMF voltage times the armature current. So we can use this expression to compute the electromagnetic torque as follows. We know that the electromagnetic torque is the back EMF voltage times the armature current divided by the speed. Well, the back EMF voltage, according to the calculation, is 210 volts. Then we have the armature current, that is 20 amperes. Okay, and we need to divide this by the speed, that is 80 radians over second. So the electromagnetic torque is equal to 52.5 newtons times meter. Okay, this is the electromagnetic torque. And well, I think that's it, no? Well, we need also to compute the speed in revolutions per minute, so we can take the 80 radians over second, and we can compute this to revolutions per minute as follows. We know that 1 revolution is equivalent to 2 pi. And also we know that, well, 60 seconds are equivalent to 1 minute. Okay, so we can, well, use this expression to compute the revolutions, and this is equal to 700 times 63.94 revolutions per minute. And that's it. No, this is the result. Okay, so this is another problem. Let's make another one. So let me go back to my presentation. Yeah, okay. So, well, let's make another exercise. Here we have the following. Now we have a 400 volts permanent magnet DC motor that takes an armature current of 100 amperes. And when its speed is, okay, the speed is 1000 revolutions per minute, okay, and the armature resistance is equal to 0.25 ohms, okay? And we need to calculate the torque produced by the motor. Okay, so again, I will write down, well, first, I think that it is important that we draw the circuit. Okay, so I will go back to my tablet, just 1 minute. Let me go to the tablet. So we need to go to this section. Okay. And let me share my screen again. Well, the screen of my tablet. I need to go here. And just 1 second. Okay, here is the connection. So I have drawn the data of the problem here. And remember that it is always convenient to draw the circuit. Okay, so we have here the voltage source that has a value of 400 volts. We have the resistance, that's 0.25 ohms. And we know that, well, we need the back EMF voltage here. And also we have the circuit. And well, we also know that the armature current is of 100 amperes. And we can apply the Kirchhoff voltage law again. So again, we need to apply the Kirchhoff voltage law to this loop. So we have minus 400 volts plus the voltage drop in the resistor, that is 1000 times 0.25, plus the back EMF voltage, that is equal to 0. So the back EMF voltage is equal to 375 volts. No, I need to redraw this because it's very ugly. Okay. So this is the result for the back EMF voltage. But we need to compute the electromagnetic torque. Okay. So again, we need to use this relationship for the electromagnetic torque that we have used in the previous exercises. We know that the electromagnetic torque is equal to the back EMF voltage times the armature current, and this is divided by the speed. So the back EMF, well, we can substitute the values into this expression. The back EMF voltage is 275 volts times the armature current, that is 1000. And this is divided by the speed of the motor. That is, well, we know that is 1000 revolutions per minute. But we need to convert these revolutions per minute into radians over second. So I will place here the revolutions per minute, and I will multiply this by, well, 2 pi divided by 60. Okay, this is the way in which we can convert directly. So if you do this, you should obtain an electromagnetic torque of 300 and 580.098 newtons times meter. Okay, this is the electromagnetic torque. And again, well, this is the problem. Okay, so I think that, well, if you can see, we can always apply this circuit when we are dealing with permanent magnets DC motors or with DC series motors. But there are instances in which you need to use other types of circuit depending on the motor that you are analyzing. So let's take a look into this exercise. Well, we note that, well, in this case, this is a Shun motor, okay? I place it here in the title of the presentation or the slide. And, well, we know the following data. First, we know that it is a Shun motor, okay? That is important for us, okay? This is not a permanent magnet DC motor or a series motor. Also, we know that the voltage of this motor is 240 volts. Also, the armature current is 30 amperes. And the winding resistance, okay, is 150 ohms. well, no, this is the field winding resistance, okay? The field winding resistance, okay, is basically referring to the shunt field. Okay, remember that the shunt motor has in series a shunt field, okay, that we need to take into account in your calculations. And also we know that we have the armature resistance that is 0.4 ohms. And we need to determine what is the, let me write here ohms. We need to determine the current in the armature and the back EMF voltage. Okay. So, well, based on this data, we can solve for this exercise. Let me go back to my tablet. Let me share my screen. So I will go here to the AirPlay, and I need to share the screen of my tablet. Just 1 second. Okay. Just one moment. One moment. I need to load the screen. Okay. So I have right here again the data of the problem. We know that we have a shunt motor, that the voltage is 240 volts. We know the armature current. Also, we know that the field winding resistance is of 150 ohms and the armature current is of 0.4 ohms. Okay. So remember that they are telling us that this is a shunt motor. So, well, we can say that here is the voltage source that we know has a value of 240 volts. Also, here we have a cable, okay? And in this cable, we have, well, we have the armature resistance that is 0.4 ohms. And also we have here the back EMF voltage, okay? And the back EMF voltage, we don't know that. And remember that in parallel to the armature of the motor, in the shunt motor, we have this field winding, okay? And we know that the resistance of this winding is 150 ohms, okay? And also the problem is telling us that the armature resistance, okay, no, this is not the armature resistance, it is the total current. Okay, the total current that we are demanding is of 30 amperes. Okay, this is the total current that we are demanding from the voltage source. So based on this, we need to well, compute the following. We need to compute the back EMF voltage and the current that is flowing in the armature. Okay. So how can we compute that? Well, we can compute what is the current that is flowing into this site, okay? That is the current in the in the field winding resistance, okay? We can compute this current. How can we compute that? Well, these two elements, no, the armature and the field winding are in parallel. So the voltage in this element should be the same, no, of 240 volts, the same as the voltage source. So we can say that the winding resistance, no, the field winding resistance is 240 volts divided by 150 ohms. And this is equal to 1.6 amperes. Okay, this is the field winding resistance. And based on this value, we can also, well, we can compute what is the armature current. What you can do to do that is to apply here the Kirchhoff current law, okay, to this node. So if we analyze here, we can see that the 30 amperes are entering the node, and this is equal to the currents that are leaving. That is the armature current plus the field winding resistance. And now, well, we know what is the value of the the field winding resistance, so we can compute the armature current as follows. This is 30 amperes minus the value of the field winding resistance, that is 1.60 amperes, and this is equal to 28.4 amperes. Okay. And well, what else we can, well, this is one of the points, no, in the exercise. Now, what else we can do? Well, we know that um, the voltage in this loop, okay, in this loop, we can, well, should be the same, okay, for the source and the armature because they are in parallel. What we can do is to apply the Kirchhoff voltage law to this loop. So, well, if we apply the Kirchhoff voltage law to this loop, we will have minus 240 volts plus 0.4 ohms times the armature current that is, well, times the armature current that is 28.4, okay, plus the back EMF voltage, okay? So basically I am considering here the voltage of the source plus the voltage drop in the resistance of the armature that we know is the resistance times the armature current that according to the previous calculation was 28.4 ohms. Sorry, amperes. These are amperes. And well, we can solve this equation to compute the back EMF voltage. And we will see that the back EMF voltage is equal to 228.64 volts. Okay. So as you can see, this is one of the complicated exercise because, well, the circuit is a little bit complicated. But as you can see, well, you don't need to use a very complex analysis, okay? You only need to remember certain facts related to the circuits. And based on that, you can solve the exercises, okay? So I will stop sharing the screen and I think that's all for this video. Later, I will upload some videos related to how we can analyze induction motors. So see you next time.